So this next slide gives you a few examples. So here you actually add, one with these three sinusoids, right? Cosine 2 pi t, cosine 4 pi t, and cosine 6 pi t. And you can look at what they look like when you take different values of phi 1, phi 2, and phi 3. Okay. So in the top curve, you're adding these three sinusoids with the phase of phi 1 equal to phi 2 equal to phi 3 equal to 0. Okay. And in the second figure, you have the case where phi 1 is 4, phi 2 is 8, and phi 3 is 12. Okay? And in the third figure, you have phi 1 equal to 6, phi 2 equal to minus 2.7, phi 3 equal to 0.93. Okay. So these values are actually given here. I'm just writing it bigger so that you can see. Okay. So you can see that, with different choices of these phases, all right, you combine to get completely different signals. Okay. So the phase information is also very important, sometimes even more important than the magnitude, depending on the application. Okay. Now we can look at another example. So this example is regarding image processing. Okay. So suppose that you have this two-dimensional black and white photo. So the value of this photo sort of corresponds to the intensity of each point on the photo. Okay. So here you have this two-dimensional signal, x of t1, t2. If this value is larger, you may see whiter values. When this value is smaller, you may see blacker values. Okay. Now you can take the Fourier transform of this to get a spectrum, capital X. And this on the right-hand side is the magnitude of its spectrum. And this is the phase. Okay. So anyway, it doesn't really, you can't really make some sense out of this. But the important thing is that, even though you cannot see visually, but both magnitude and phase seem to actually contain a lot of information. Okay. So to verify this, right, you can try to take the same magnitude, but then eliminate all of the phase information. So if you just set the phase to 0 for all frequencies, then the resulting image that you get is this. Okay? So originally it's this, but if you get rid of the phase information, you see something that is completely blurred. Okay? So phase information is actually very important for images. So here you get the time domains, this x of t1, t2, with the phase set to 0. Okay. And the reason for that is because, when you observe these white regions, which correspond to very large values of x, or the black regions, which correspond to very small values of x, and when you look at these edges, right, these edges means that the value has an abrupt change from small value to large value, or the other way around. So these things, right, extremely large values, small values, or these edges, rely on different frequency components to be added in a very specific way, right? You have to add, so for example, for these really bright regions, you need all these sinusoids to aggregate so that they have, large constructive gain, okay? And for these edges, right, you need their phase to be aligned well enough so that they add up to have this very sharp transition in a short time. So if you get rid of the phase information, then all of this goes away, right? Your frequencies are no longer aligned in the way corresponding to the information of the image, and therefore what you see is something really just blurred, okay? All right. Now in this image here, what you see is, a figure where you sort of eliminate the magnitude information, but preserve the phase information, okay? So in this case, what you do, right, you're looking at a signal with constant magnitude in the spectrum. Okay? So you can see that when I eliminate the magnitude information, right, we have less of this transition between white and black, right? A lot of these grayish regions sort of go away. But because we're aligning these sinusoids in the way as perfect as in the original figure, therefore we can still sort of observe these edges in the figure, okay? So for visual images, the phase information actually contains, a lot of information, okay? Now what this other experiment is doing is that they're replacing the magnitude of this image with the magnitude of this image, but combining with the phase of this image, okay? So if you combine the magnitude of this image with the phase of this image, you get something like this, right? And you see that because this image sort of still preserves the edge information of this image, so you can still sort of see this image inside here, okay? Even though the shading color is a little bit different. Okay. Anyway, so this is just an example to give you an understanding of how the magnitude and phase may impact what we see, okay? But in certain other applications, magnitude may be more important than phase. For example, in audio systems, right, for the signals that we hear, the magnitude is often more important than the phase, okay? So it really depends on the application. Okay. All right, so anyway, going back to this magnitude and phase representation, right, so previously we looked only at a particular spectrum, right, the spectrum of a particular signal, okay? Now, suppose that we take the signal and pass it through a linear time invariant system with frequency response, capital H. Then by the convolution property, we get this relation between the input and output spectrum, okay? And this is true for both continuous and discrete time. So again, we're interested in looking at the magnitude and the phase, okay? So if we write this in terms of the magnitude and phase, we get the magnitude of H times the magnitude of X times e to the j, the phase of H, okay, times e to the j, the phase of H, plus the phase of X. Okay? So this means that when you pass a signal through a linear time-invariant system with frequency response capital H, the magnitude of the output is equal to the magnitude of the input times the magnitude of the frequency response. And the phase is the phase of the input plus the phase, added upon by the system to get the phase of the output. Okay? And this is quite intuitive, right? Because as we mentioned, this is the magnitude of the frequency component, omega, for the signal. Okay? So when you multiply with the magnitude of the frequency response at this frequency, right, it basically tells you, how much you should magnify this frequency component of the signal. Okay? So this magnitude of a frequency response is referred to as the gain of the system. Okay? Because it tells you, how much you should magnify this particular frequency component of x. Okay? And suppose that your original signal already has a certain phase, then when passed through the system, it imposes additional phase depending on the frequency response. And therefore, this is called the phase shift of the system. Okay. Now, if your system provides a linear phase, right, this e to the minus j omega t naught, then as we mentioned here, this linear phase means that you're shifting every frequency component by the same delay. Okay? So when you impose a linear phase, a phase that increases linearly with the frequency, then you're actually imposing a delay t naught because you're shifting every frequency component by the same amount t naught. Then when you add them together, you just get the original signal, the aggregate signal, still shifted by t naught. Okay? So the same shape of the signal remains, it's just delayed by t naught. Okay. Now suppose that you have a nonlinear phase. Nonlinear phase means that now every frequency component is no longer delayed by the same amount t naught. Okay, so different frequency components may now be delayed by a different amount. So when you are delayed by a different amount, the different frequency components no longer, adds together in the same way. So the shape of your signal now will become distorted. Okay? So this is an example here. So suppose that this is x of t. Then if you pass it through a system with a linear phase, right, so suppose you pass it through a system with a linear phase, okay, you will get something like this, right? So the shape does not change, but the signal is just delayed by t naught, which is 10 in this case. Okay. But suppose you pass the signal through a nonlinear system, a system with a nonlinear phase. Okay. Then every frequency component is delayed by a different amount. So when you add them together, they are no longer aligned the same way as before. So the shape of your signal actually, changes. Okay? Right. So, sort of imagine that, suppose this is your input signal, okay? So if you pass this signal through a system with linear phase, okay, then this signal will just be entirely shifted by the delay T0. But if you pass this through a system that has a nonlinear phase, then this means that every frequency component will be delayed by an amount that is not proportional to its frequency. And therefore, when you add them together, you may get a different mixing of something like this, right? So the shape can completely change because of the different alignment of these frequency components, okay? All right. So, right, this last one is just, delaying this by a certain delay T0. Okay, so this is not that interesting. Okay. So you can see the same thing in discrete time signals as well. So here you're passing a signal through a system with linear phase shift. So you'll get this same shape, just shifted by 5. But if you have a nonlinear phase, then the shape of the signal actually becomes distorted. Okay. All right. So when you're looking at a system with a nonlinear phase, right? So a system with a nonlinear phase gives you a phase shift that is not proportional to the frequency of the signal. Okay. But still, we would like to see, what is the resulting delay that is caused at each corresponding frequency component. Okay. So we can do this by taking the first order Taylor approximation of this phase shift of the system. Okay. So if you take the first order Taylor approximation, all right, this will be equal to the function evaluated at this particular frequency omega naught plus the first derivative evaluated at omega naught times omega minus omega naught. Okay? So we're doing a first order Taylor approximation of this nonlinear phase. Okay, so suppose that your original phase looks something like this, right? This is extremely nonlinear. So we want to know what is the impact on the delay of each, group of frequencies around a certain point omega naught. Okay. So we want to know what is the resulting delay occurring at frequencies around frequency components around this omega naught. Okay. So the way we do this is we look at the first order Taylor approximation around this point. Okay. So the first order Taylor approximation about this point gives us this formula here. Okay. So let me group together the constant terms, right, which is this plus the slope times minus omega naught into this phi minus phi. And we set this slope as minus alpha. Okay? So phi is just, minus the angle at omega naught plus the slope times omega naught. And alpha is just minus the slope at this point. Okay? So according to this first order Taylor approximation around omega naught, you can see that the frequency omega naught experiences a approximately linear phase shift, okay, that scales by alpha. Okay? So when you have a phase that scales with alpha, which is T0 here, this means that the phase shift is causing a delay of alpha to the frequency component around omega naught. Okay? So this delay we call the group delay, okay, because this is the delay that we observe approximately among the group of frequencies around omega naught. Okay? So this group delay is alpha, which is minus the derivative of the of this phase, of this nonlinear phase about the frequency that we're interested in. Okay? Okay. So again, what is group delay tau of omega? The group delay tau of omega tells us, how much the frequency component around omega is delayed due to this nonlinear phase of the system. Okay? So if you're looking at different frequencies, you will see that the slopes are different, right? So this means that different frequencies will experience a different delay, okay? So when different frequency components experience a different delay, then like I mentioned before, when you add them back together, they no longer align the same way as before, and you will see distortions to the signal.